There we go. Okay, let's get started. As always, I insist if you have questions, please you can go in. You can go in. You can use the chat room, or you can raise the hand. Given that I've muted all of you, you could raise your hand, and after raising your hand, you can always ask your question. Mr. Casidio, you have already raised your hand. Okay, this is not a good sign of starting. Okay, let me see what you've written in the chat. Still requesting for the link of the previous recorded lecture. Yes, you will get them today. That is Murindo. I think that is the question Casidio wanted to ask. Someone was saying, link. Okay, actually this man Murindo will give you the link today. I may even, because I know he's around the campus, I may just request him to come and give him, I was trying to create an account on MediaFire so that I simply give you a password to that account. You go and you access those materials from there. That's what I was thinking of. And I got frustrated in the morning. But if it is so urgent and Melinda can catch up with most of you, yes, I said MediaFire Mumbere, and you're repeating what I've just said. Okay, I'll share the links or the recordings. I'm going to talk to your coordinators. I'll interact with Raymond and Sonia, and they should be able to give you those links by the end of today. And I'll also upload some of them, not on Mwere, because I've been having some issues with Mwere, but I've created an account that I was using for other things, but I think I can throw some of those files there and you access them. I'll only have to give you the password to the account on condition that as soon as you access them, you don't delete them so that all the other members who want to access them can find them there. I'll just try to, first of all, convert them because the sizes are so huge. These lectures run for over 2 hours sometimes, so you find that the file is super huge. So they need to reduce in size a little bit. They need some kind of compression before they can be shared, especially if they are going to be uploaded. Okay, let's get started. This example 4, we had actually discussed it last time, but I think we did not complete it. And if I recall, I don't know, I think I had some kind of power interruptions. Of late, we have been having lots of power interruptions. I think there is some probably the maintenance or there are issues around the campus. Perhaps it is in my college, I don't know. But I guess today we may be fine. So I had gone through this, maybe we had finished it, I don't recall, but I can start with it and we'll go through it a little bit fast because this is material you're now comfortable with. So for starters, we have this problem here, which is solving this second order differential equation using the power series methods. And this time around, we are saying it is about x equal to 1. All the other examples we are dealing with x equal to 0. So because of the x equal to 1, remember from our definition, which is this one here, this is the definition we have. From this definition, you realize that every time we had to solve any given equation about x equal to 0, this x naught here would go to 0. So would only have an, then would get x to the n. Then we'll quickly solve this one. How? We'll differentiate depending on the order of the differential equation. And then we'll substitute. But this time around, we have it as x naught, which is equal to 1. So since the x naught is equal to 1, you are dealing with the air potato. Since x naught is equal to 1, in this particular example, we can, when you substitute, you have x minus 1 to the n. But now, if we let the whole of this term be a t, that's what you are trying to do, then we can have a change in variable. It means if we change it to t, we have a t which is x minus 1. This is the change of variable. And what would that mean? If that's the case, we can substitute into this one. Of course, when you change it run from rather the whole thing to be t, you can redefine the other terms as well. Depending, the limits will not be affected. They'll still be the same. So we have y, which is an, t to the n. The whole x minus 1 is t. We differentiate this, we get the usual expression. The only difference is for all the previous examples, it was in x, given that the x naught was 0. But now that the x naught is 1, we have substituted this to be t, and everything is in t now, the whole of this statement. So we have the first derivative, the second, rather the first derivative and the second. And then once we have that, we can do the necessary substitutions. And when we do the necessary substitutions, so we have this, we substitute it into that one there. We are going to just substitute the whole of this one here into 1.21. And when we do that, we end up with this equation here. That is this one here. We are substituting into this. So remember, it was y prime prime. So the x minus 1 is t. That's why in here, where we had x minus 1, it is now a t, if you look at this one here. So we substitute. We know this is t, that is 2t. So we have y prime prime, which we have already differentiated up there. We ended up with that is the previous one here. That is the n minus 1 n t to the power n minus 2, and then we have this. Now that you have the notes with you, you can follow closely. So when you make those substitutions, you end up with we end up with this one here. So that is a direct substitution of the derivatives into this second order equation. And on doing that, we simplify. So the first thing is, since there is a t, we can take this t inside. This t here, we push it inside here. When you push this t, remember it is t, t goes in, you have t to the n minus 1. Then you're multiplying this with a t to the 1. Of course, this one and that will cancel, so you get t to the n. That's why from this step, you have here a t to the n, this one here. Okay? The others remain the same. So we just remain with this minus 2 out here, but the t goes inside. Okay. So on getting that, we can go ahead and we say now from this statement here, I told you how we go about this. I've overemphasized that. That if you have this now, the first thing is you look at the powers. This is n minus 2. This is n, this is n. For the powers of t, we don't have to worry about this series and that series, but we have to only worry about this one. So it means we start here. We always start by unifying the power of t. So from here, since we have it as t to the n minus 2, we can make a change there. And we say if we let m be n minus 2, so we substitute where there is n minus 2, that would be m. I told you you can have multiple substitutions here. So it means that can be m. But remember, if our m is n minus 2, if this is n minus 2, then we can get a substitution for the lower limit. But now remember, the lower limit here runs from 2. So it means this will be 2 minus 2, and that will be a 0. That's why in here it is running from 2, but when we implement those changes, it now runs from a 0. So instead of running from n equal to 2, it is now running from n equal to 0. Then we can substitute into these ones here. M is n minus 2. We have seen that if now this runs, if we change this to m would be 0. So you can, where you have this n, if you let it to be m, the whole thing can be m here. But after substituting m and the whole of this statement is in m, if the whole of this is in m, then you can again take it back to n. So I meet those several substitutions, and once I say this is m, I immediately take it back to n. That's why you see it is appearing as n, but that is now the n substituting, being substituted back into m. Okay. So how do we get this one now? From in here, we know that this is n. So what do we get? So if we clear this one here, I think we've understood the 0 there. Now we can look at the n. We have n here and we have n minus 1. So what is n? If you make n the subject here, n would be m plus 2. That is this one here now. If you see this one, that one is this part here. Remember, we substituted m, so this n here, what is becoming n minus 2 is this n here. That n in the small circle is what has become the n plus 2 here. Okay? Then we have n, but remember this n minus 2 is actually m plus 2. It is this m plus 2 here. It is this one. This links into that same arrow. But remember, when you take it in m, you substitute it back into n. So that is this one here. Okay? Then we have n minus 1. So what is the n minus 1? Our n minus 1, we now have this n minus 1. So we have this n minus 1 in red. What does that n minus 1 become? Remember, n is m plus 2. Where there is n, we put m plus 2. And there is a minus 1, so this is minus 1. Now when you simplify this, it becomes m plus 1, implying that this m plus 1 is what appears as n plus 1. But remember, this n plus 1 is now what appeared originally as n minus 1. So this one should be linking into this one here. which gives you that one there. But remember, when we say it is m plus 1 here, we take the m back to n. So it becomes n plus 1. If you can do it in one go, good for you. If you want to make those several substitutions, no problem. You just have to have speed, because when I'm calculating time spent on these numbers, I don't allocate time to those multiple substitutions that add no value to the computation. So that will be your personal choice. If you know you may confuse the substitutions, then you first substitute m can become k can become I, and then in the very final step, you take things back. So you'll have some kind of bulk write-up, but at the end, whatever marks will be awarded is what you'll jump away with. Okay, I think that one preempts is that. And then what is n? N, we have some small n here. We have a certain n here. There is now this small n. But remember, we have said the n is m plus 2. That's why you see that now this m plus 2 comes right here. You can see it is now an plus 2. It first of all becomes m plus 2, then the m is taken back into the n, which is an plus 2. I think we are clear there. I can now remove all of these without issues. Okay, so in that case, how do you go about the other substitutions? It is the same story. Now, when you come to this one, same story. Rather, this one, you don't have to change anything, given that this is n now, this is n, and this is n. The only thing we need to fix are now these zeros. We need to upgrade this one, and we also need to upgrade this one here. Why? It's because this is n is equal to 1. So we cannot lower this. We just have to upgrade this and this. So how do you do that? Remember, n runs from 0, 1, 2, and it continues all the way. So what we do is we can substitute only n is equal to 1. So if we do that, and we take in only the first one, we can substitute only this one here, because it is already. And if you do that, it means when you throw here n equal to 1, this will be 1, this n becomes 1, this n also becomes 1, this n becomes 1, and this n here becomes also 1. So what do you do? What do you get? This is 3 times, this is 1. We have, oh, yes, we are taking this one to 1. Sorry, we are taking this to, we substitute 0 here so that everything runs from 1. Sorry about that. There is a small mistake I'm making in my explanations. I need to repeat that. We are saying n runs from 0. This is 1, 2, and it goes all the way. So since this runs from 0, we can substitute the 0. So basically what we are doing is we can throw in the 0. We can substitute this one in so that we standardize. When we do that, then we will force this one to run from 1. And even this one to run from n will go to 1. That's what we are trying to do. So firstly, we simply take in the 0 for this and that so that the limits can be the same. We make the limits uniform. So if you do that, you simply substitute a 0. So this n is now 0. This n is also 0. This n here is 0. And of course, this n here is also 0. If you take that, it means now once you substitute the zeros, you'll have the 2n0. This is the 2. 2 times 1 is 2, which is that one there. Then this one you remain with the 2 because n is 0. then what do you remain with? We can now sum from n equal to 1. So this one is upgraded from n0 to n1 here. This statement is the same as that. Then we do the same here. When you take this n here to 0, and then that n there to 0, that will be 2n0. That is this one here. Because this t to the 0 is 1, so you have a0, which is this one here, times 2, which is that. Then we sum. This is n from 1 to infinity, this one here. So you realize that if we do that, we now have this n is the same as that n, which is the same as this n here. That's what we have now. Okay. So from this, we can go ahead. From this, we realize that now, since this is the same, we can easily simplify. The power is the same, and the limits are the same. So since that is the case, first of all, we've combined this one here with that one there. That is this statement here. This one is taken with this one here. Okay, to give us that one. Then we combine the balance into one sum, which is this one here. We've combined it into one sum. That is the sum n running from 1 to infinity. We have this whole term here. This one here. an plus 2. That is this one here. Then we subtract 2 into this one. So basically we are taking the t to the n out, since it is the same for all. That is this one here. Then we have 2an, which is this one here. We equate to 0. Okay. Doing that brings that to closer to the final steps. So in here we equate the coefficients. So if you first of all equate, since this is t to the n, we can consider this as 1, but we have these two here, this and this. If we equate, now we have t, remember we had substituted, so if you deal with the coefficients of t to the n, that would be, this term here will be equal to 0, since these ones don't have t to the n. That is this part, and then you'll have this whole thing here, which will also be equal to 0. So we have these ones, if you have t to the power 0, if you just took the whole of this and you have it as t to the 0, then you'll end up with this one here, since there is no t here. So it's like you have this whole thing. Then this is a t to the 0. T to the 0 is 1. So if it is 2 to the 0, you'll have this term here, which is that one there. And then you equate it to 0, this other side on the right. That is that. You end up with this small equation here. And then when you take coefficients of t to the n, you'll basically have the whole of this, and you make an plus 2 the subject. So we take this whole term out, this one, which is this one here, is the whole of this. If you take this one is from there, then you make an plus 2 the subject. That is what we are doing here. That gives us this. Remember, this will be equal to that. This goes this way. That is the numerator here. And then you'll divide by n plus 2, n plus 1, which is that. But remember, we had already substituted in here. The series runs from n is equal to 1, from n equal to 1, n equal to 1, n equal to 1. So since it runs from n equal to 1, n equal to 1, n equal to 1, it means that in this step here, n should be starting from 1 and onwards. So we condition it here, which is obvious given what we have done there. This is picked from the fact that these n's are all running from 1. Okay, once you get here, you are basically done almost. And this shouldn't be anyone's kind of problem because it is quite direct. So simply substitute here. You can pick values from n equal to 1. You can go up to n equal to 6. Here we stopped at n5. And when you do those necessary substitutions, you'll get these here. So if n is 1, you throw here 1. N is 1, n is 1. This denominator, rather numerator, will be 0. So you end up with a 3. Remember, n1 here gives you 3. You have 1 plus 2. You will have here 1 plus 2, which will give you a 3. That is this one here. What about this way? N is 1. If n is 1, this numerator is 0. So the whole numerator becomes 0. 0 over that is 0. That's why we say A3 is 0. We go to N2. If n is 2 here, you'll end up with F4. N is 2. This will be equal to 2an. That will be 2an. But remember, what is n? N is 2, so that is 2a2. And this will be over, this is 4 times 2. That gives you a 6. And then since you have a 6, what is a2? We have a2. Remember, this is a2 here. What is our a2? We had got that in the previous statement. A2, we have our a2 here, which is our a2 is right here. A2 is minus A0. So what does that mean? That means that now what we have as F4 will be equal to, this is 2 over that, which should be a 1 over 3. I don't know where this is very correct. Hopefully it's not me making the mistake. We will look at it. So what is this? This is 2 over 6, which is a third, times A2, but A2 is minus N0. But then the question is, okay, that is minus N0. I don't know whether this is correct. I could be wrong, but I see as if it is a third N0. Maybe there is something I'm missing out. This is probably a third N0. I could be wrong. I need to check it out. We have this, we have that. Did I make a mistake anywhere? I see it as if it is a third N0, but I could be wrong. I see a 2 over 4. I don't know where the things are coming from. Let me check it out. Okay, maybe we made a mistake here. Let's first study this. The minus comes this way. Hopefully it is a minus, not a negative. Then we have, that's that. This was a 2. That was a 2, so 2, 2. Okay, I think the mistake is somewhere here. I've seen the mistake. This is a 2. This is a 4 here. I think that's where the mistake comes from. This is a 2, this is a 3. And this is a 12. Okay. So if it is a 12, right, this is 12 over what? This is a 2, this is a 2, a 2. Then this goes with that one, which is a 1 over 6, a 2, but a 2 is minus a 0. So this is minus a 6th N naught. Okay. That seems fine. The mess is here. This is 4 times 3. This should have been 12, I think. I don't know why it is a 4.3. The issue is somewhere here. The cavuyo is somewhere there in the denominator. Okay, I think we can continue. I don't have to do the rest, guys. The rest you do the same thing. So the rest should be appetizers for you. You do the rest. When you do the rest, check out my answers. They may be wrong, they may be correct. My mistakes are your responsibility. So you go through these others, N3, N4, N5. If you do that, you end up with all of these. So we have our interest is in F3 is 0, F4 is that one, and then you have F5, which is 0. S6 is minus 1 over 30 N naught, and S7 is 0. So what we need to know maybe first of all is that what we need to quickly know is that F3 is equal to F5. This is F5, which is equal to S7. And all of those are zeros. Okay, so since all of those are zeros, when we expand this in t, remember the t is x minus 1. Don't forget that our t is x minus 1. So if you substitute, before we substitute the t back, the x minus 1 back, when you expand this, it will give you that. And when you get this, it is in t, we have all of these coefficients for A0, A1, this is A2, okay, A2 is minus A0, and then A3 is minus 60 A0, then we have that one there. So when we substitute into those, remember some of them we are supposed to be zeros. So of course, when you take the zeros will come out. That's why when you expand, if you check out this, you realize F3 is here. This one will go to 0. That is our F3. We have F5. Of course, if you continue to get F5 and S6. So we just have to substitute for F3. When you substitute for F3, this whole thing goes to 0. That whole statement goes to 0. That's why you see in this expansion here, there is no t to the power 3 because of this F3, which is equal to 0. So when you substitute now that into this, you end up with this statement here. Hopefully my signs are correct. Hopefully, I take the N naught out here. When you take the N naught out, you get that. We need some. We need to rearrange this in terms of N naught and A1. This statement here. So you have this N naught. I'll first of all highlight the N naught. This one is N naught here. This one is N naught. This one is also N naught. And this one is N naught. So you take those ones out. If you take those ones out, that is when we factorize. Just consider the ones in the purple. This one here, this one, and this one. So when you take the N naught out here, that will give you the 1, this positive 1. Then we take this N naught out. The N naught is out. That's why we have a minus t squared because of that one there. Then we take this N naught out. That is the minus 1 over 6 t to the 4. That is this one here. Then we take this N naught out, which is the minus 1 over 30 t to the 6. So you realize that this one will peak in terms of even powers for this one. This is even, this is even, this is even, 0 was even, and then you add it as A1. And remember, if you have t to the 0, that would be A1, which is somewhere here. Then this is a plus. We have now the A1t, which is this one here. So once you have this, you take it back in x. Remember, t is x minus 1. So we take it back and we get the general equation. So what is that? That gives us this statement here. If our t is x minus 1, you throw it back, you end up with the two linear independent solutions. But remember, one is in terms of A1 and the others are in terms of A0. Here, we said if you have two linear independent solutions, from what we did last semester, the generic equation would be C1y1, where 1 is the first linear independent solution, and then this is plus C2y2, y2 being the second linear independent solution to the second order differential equation. So in that case, what we call y2 is this one here. But in this case, the C1 is the A0, and the C2 here is the A1. This one is the A1, and that one is the A0. If there are some initial conditions that are attached, then these values can be determined in a more specific way if the problem is kind of linked to an initial value problem. Okay, and this is where we are saying, oh, not change of variable is merely for convenience. The problem could be yes. This one depends on your enthusiasm. Some of you are over enthusiastic. So if you're enthusiastic, you can just substitute, you differentiate with your x minus 1, you still come up with the same answer. But they say if your head is weak, then you should always sharpen the axe. Those are not my words, but they are biblical. The weak are always advised to sharpen the axe because they use a lot of energy to solve would-be simple problems. So since for me, I am not weak, I have taken the substitution t equal to that. But for you, the strong, you can leave it as x minus 1. Okay. I think that one ends that example there. And once we have done that, I guess we've done most of those examples. I'll clear this. And I don't know whether they are... Okay, I see something in the chat. What are these people saying? The denominator is 12, not 6. Yes, thank you very much. I was struggling to figure out that. Someone helped me figure it out. This is Morris Jagokori. Okay, then we have Rashid Kiwewa. It's okay, it is 1/6. All right, okay. I think you have no questions on that. So if there are no questions, I think that is it. These are just some remarks guiding what is happening there. Then you can solve this differential equation. Okay, now the difference with, if we compare this, we have some initial value problems, but please be mindful of the comments we are making. That was one. We said if you have an initial value problem, I've already said if the problem is an IVP, then you can get a particular case. The partial solution may be solved without specifying the so okay, that one I have already preempted. The number of terms to store part while computing the recurrence is not big enough. Is not big. It's not a big problem to think about. Okay, in general, we compute enough coefficients. Someone asked us the other time, how do you tell the value of n? at which you should stop. I think this is the answer we are trying to give, that since you are making approximations, remember you cannot exhaust n, so you can go as far as the approximation can be appropriate for whatever you're trying to estimate. So any value pick off, but sometimes for consistency, they could tell you expand up to n is equal to 7, meaning everyone must now follow what has been suggested or what has been specified. So in the second example, these are the same things. I'm really not going to waste much time here, but the difference here is in the difference is in the fact that here you'll not get a general solution, but you'd rather get a specific solution, or call it a particular solution. If you look at this here, we had a general solution because you have constants. We have constants in here, that is A1, this one here, and then we have A0. So in the other one, A0 and A1 will just disappear. Okay, so in that case, what we end up with, so that is the only difference between what we have been doing and this example. And surely here I don't have to take any much more time. So this is the problem you have. Simply substitute. This is this and that. But there is now something you need to take care of here. Remember the other one, they would tell you about x will equal to 1, about x will equal to 0. In this case, we don't say solve the differential equation about x will equal to this. Why? That x is implied. You simply pick it from this and that. Remember, these are written as functions of x. This is y of x equal to something. So what does that mean here? Here it means for this statement here that at x equal to 0, or when x is 0, if this x is 0, then y is 0. Then here we are saying if x is 0, that is this second one here. If x is 0, y prime is 1. So what am I trying to say? That here they are not saying about x will equal to 1 or about x will equal to 0. That information you pick it from these initial conditions. So this one here is about x equal to 0, meaning your x naught will be equal to 0. Okay? For those who may be a little bit lost, what I am trying to say here, or what I am trying to emphasize, is that if you look at the previous problem, we said about x is equal to 1. You see that theory there, rather example 4. In example 3, we said about x is equal to 0. This is the scenario we are having there. Then in the second example, we said about x is equal to 0. That is this one here. But when you look at example 5, in example 5, right here, the about is not there. We are simply saying solve the differential equation is this based on those initial conditions by power series method. So the about, as I've just explained, we will pick it up from y0 and then this one here. Okay. So we can continue. We can continue with this one here. So in this case, if we are to continue with this one, okay, someone is saying, I saw some question here in the chat. What has happened to my chat room? I had seen some question. All derivatives are normally examined at the same point. I think these people are arguing. TS doesn't make a sense. Okay, I think these people are having a conversation. This is a conversation between Kasirie and Namunguba. Okay, I think they are trying to sort out some more misconceptions, which is okay. All right, let's continue. So this is what we have here. Yes, in this example here, I am saying that we don't have to, all of the other steps are the same. So I'll just continue normally. As always, this is by definition. By definition, this is what we have. Then you differentiate and differentiate, you substitute. That is the same old story, the usual case. And if that is the case, you are now experts in those things. Same old story. What happens here is that here you have n minus 2. This is n minus 1. You must take all of those to n. And then after doing that, you see you can take this one and this one. The x squared here goes inside. So you have x to the n minus 1, and then you have that 2, which becomes this one here. You make several substitutions there until the powers of x to the n are the power of x is the same. You can see they are the same. Then here you have one small problem. What is that small problem? The small problem is on this one here in blue and this one here in blue. Why is it a problem? This one is n equal to 2, but this one is n0 and that is n0. So what you do here is you substitute. You can substitute n0 and then you substitute n equal to 1. When you substitute n0 and n equal to 1, then it means that, so here you have n, you take n equal to 0 and you also take n equal to 1. So that if you substitute 0 and 1 in this one here, 0 and 1 in that series, then everything can run from n is equal to 2. And if you do that, which you are now good at, you end up with this, and then when you rearrange, you end up with that. You compare the coefficients, you end up with this one. Then when you come here, where is my pen? Okay, so when you come here, you substitute back and then you get this one here. That is the statement right here. But now from that, remember you have a y and you can differentiate the y. So remember I had y prime and then y, the initial conditions. We had the two initial conditions. Those of you who still remember, and our initial conditions are indicated, they are here. Our initial conditions are here. They have resulted into that. The initial conditions y0, which is equal to 0, and then y prime 0, this is equal to 1. Okay, so we have first of all our y from what we've got there after substituting. I'm hoping we are together. When we made the necessary expansion and substituted, we got this one here. That is this one here. That is the first one. Maybe I can highlight it in, I can highlight it in red. This one, the first one here. Can underline it in red, this one. Okay, so what happens there is, we know if you consider the first condition, this one, which is y 0 is equal to 0. That is the first condition we are dealing with. What does this say? This one says that when x is 0, comma, y is 0. That's what this condition is saying. So when we come to this, before differentiating it, what do? We know x is 0. So everywhere there is x that is 0, of course the x squared will be 0. This one here, what is that? X, all of these x's, this is 0, this is 0. All the way it will be 0. You remain with the n naught. But remember, we are saying when x is 0, since this starts from n naught, y is 0. This y is also 0. So all of these from here, they are zeros. We remain with only n naught, which is equal to 0, which is this term here. Which is this term here. It is this one. Then, what we do is we differentiate now this term to get the y prime for this part here. So when you do the y prime now, we differentiate this first term here. That gives us what? So we are differentiating this one. When you differentiate this, what you get? Differentiating this with respect to x, of course, this is n naught. The n naught becomes 0. So we start with a1 now. When you differentiate this whole term, I think I need to paint. We are differentiating this one here. If we differentiate that, so if you differentiate the n naught, that becomes 0. We are differentiating with respect to x. You will have a1 here. This will be 2a2x. This is 3a3x squared. This is 4f4x cubed. And you continue. Now that we have differentiated, we have to throw in the initial condition. Which initial condition? We have to throw in this initial condition here. What does this condition imply? This initial condition is saying that when x is 0, comma, y prime is 1. So what does that mean? That means that everywhere we have x will throw a 0. So this will be a 0, this will be a 0, this will be a 0. So this is 0. This whole thing here is 0 because of x. This whole thing is 0. We remain with the a1. But we are saying x is 0, you remain with the a1. But y prime, because of this condition, y prime is 1 when x is 0. So this y here is equal to a 1. So that's why we say that our a1 is equal to a 1. That is what we are saying there. That is our a1 is equal to A1, but remember we had already got the A0 from the previous one as a 0. So since we have A0 and we have A1, we can now come and we substitute here and we get to the A3. So what is A1? A1 is 1. So if you substitute this A1 and you substitute it there, if this A1 goes there, it means that our A3 simply becomes a minus 4 over 3, which is this one here. Okay? And from the general statement, so we have A3, you can now substitute direct until you reach this part here. Now, if you know A3, you can go ahead and you get the expression for F4. If F4 is in terms of A3, you substitute this one here. So when you substitute all of those terms back in there, that will now take you to what we have down here. That now you equate the coefficients and you have this, you have an, which is this statement. So what you have to do is you substitute the a's that have been established using the initial conditions. And if you do that, you end up with these terms. So you have an plus 2, you have the whole of this here. But remember, our sum, guys, runs from 2. We are summing from 2, all of these ones here. The summation goes from 2 here, and from 2. So because of that, in here, you can see that when you look at this step, this one here, we run from n is equal to 2 and onwards. So now we throw in n is equal to 2. When you throw in n is equal to 2, this is your n is equal to 2. This will be 2. That will be, when you throw a 2 here, that will give you F4. Then n is 2. That will give you 2. N is 2 here. This is 2A1. Then minus 2A2. That is this one here. This is over n is 2, that is 4, n is 2, this is 3. So when you substitute n is equal to 2 direct into this, it gives you this one here. And what does this simplify to? Remember, we go to the A1. Our A1 was 1. A1 was equal to A1. And what was A2? We can go back above there. A2 is 0. Check out this, guys. A2 is right here. A2 is here. A2 is 0. That is the A2. A1 is 1. A3 is that one there. So if you do that, and you go back into our substitutions, in here, you realize that A2 is 0, so this whole term here goes to 0. We just cancel out this one. That whole term goes to 0. That whole term is a 0. Why? Because of the A2. So you remain with the 2A1, but A1 is 1. That is the 2 over this one here, which gives you 1 over 6. So you can see this time we are getting 1 over 6 without any coefficient. Then for n is equal to 3, same story. When you do the necessary substitutions, you have n is equal to 3. We are substituting into this one here. So if our n is 3, this will give us a 5. N is 3, 3 minus 1 is 2. That is 2 times 2, which is this one here. Then n is 3 here. 3 minus 1 is you get n at 2, which is this one here. And that is minus 8. N is 3, that is 8 at 3. Which is this one. Then n is 2. Rather, n is 3. If n is 3 here, 3 plus 2 is 5, which is this 5. N is again 3, 3 plus 1, that is the 4. But remember, A2 is 0. A2 is 0. So since A2 is 0, this whole term here is 0. We remain with minus 8 A3, but we got A3 as a minus 4 over 3. Okay? So you can simplify this one. This 4 here, this 4 goes here once, and here you get a 4. I think we are together, not a 4, but rather a 5. That 4 goes with the 20. 20 times 5, sorry, rather 20. 4 times 5 is a 20. So this couple here goes into 25 times. So you have here your 8. This is 8 over 3, but 3 times 5 is 15. Then you have this minus here. You have this minus going with that minus there, which gives you the 8 over 15. And once you have that, we can now substitute back. So we know A3, we know A5. We can substitute now into this guy here. Maybe I highlight just. Okay, so we now have this guy here. This is the guy we have. Okay, so when we substitute, remember A0 was, do I remember what A0 was? I think A0 was 0. You can check here very fast. We got A0. A0 was 0, it is here. A0 is 0. A2 is also 0. A1 is 1. Okay, so that one gives us what we want. So it is this one here. So A0 is 0. So since the A0 here is 0, the A1 is 1. This A1 here is 1. A2 is 0. A3 we have just got it. A3 we got it as minus 4 over 3. If you remember, this one was minus 4 over 3. F4 we have got it as this 1 over 6. And then F5 we have got it as 8 over 15. Okay. So if you have those two, rather you have these, you simply substitute them. And when you substitute them back, you get the final solution as that one. Okay. I think we are done with that one. There are no questions. We continue. So we can continue. How do we continue here? We say, you can clear this one, I think. Okay. So that one preempts that. This other example I am not doing. Now there is this example here, same story. You have y1. This is now this is about x equal to 1. We are approximating. When you are approximating, you consider the initial condition now, which is being imposed. So in this case, this is 1 and this is 1. So this will be about x will equal to 1. So this will be about x equal to 1 because of these conditions here. And you'll end up with a specific problem. The other things are the same. The only thing you need to think of here, you can use identities. Maybe I can illustrate that a little. Yes, you guys, can you hear me? Okay, hopefully you can hear me. Can you guys hear me?
Yes, we can hear.
Yes, we can.
Can you see my screen as well?
Yes.
Good. I don't know what happened. I had gone off. I think some of you who are psychics and voodoo practitioners, I don't know what you had done to my network, but they say God reigns, so somehow I am back to the annoyance of those who had wanted things to jam forever and the lecture ends. We are still stuck together. All right. Tuendelee. So let me again mute you all. The gossipers, I am going to silence you. Okay, so let's continue. In here, I was talking about this example. This example is basically the same thing we have been discussing. There is only one small technique that I'm going to throw up here, which is really easy for you to figure out. It's not a big deal, really. But nonetheless, we can unpack it together. So one, I was trying to, I need, where is my power disorganized me? Okay, there we go. Right. So I am saying, first of all, I was commenting on this, that now this will be about x is equal to 1. We have seen how we deal with that. You can make substitutions if you want. If you don't want, you can go direct. I told you it is all about your enthusiasm. And if you are so lousy that you don't want to make those substitutions, then you sharpen the axe, because it will call for a lot of work. Now, Guys, please pay attention. Now, what is the key here is, since this is x plus 3, you need to look at this a little bit more carefully. This x plus 3. We are saying this is a non-homogeneous kind of differential equation. And I think what we've been dealing with on the other side, if you look at example, if you look at the previous example, this is 4. You can see 4 was homogeneous. It was equal to 0 there. Rather 5 was homogeneous. 6, rather 4 was also homogeneous. 3, I think, was also homogeneous. Where is 3? 3 is somewhere here, homogeneous. And I think 2 was, okay, all of them were homogeneous. Now, in here, we have one which is non-homogeneous. Okay, number 6 is non-homogeneous. And usually, if a problem is non-homogeneous, remember how we dealt with the non-homogeneous equations the other time? We would say this is a polynomial of order 1. That is what we did last semester together in engineering math 2. Then we solved these equations here by getting a generic expression that you would differentiate thrice, and then you substitute into this. Then you get what we call the YP and then the YC complementary. And then we got the particular, and then we would combine them together. Then we also discussed the principle of superposition. But in this case, when you deal with approximations here, first of all, I've already told you that this one will be about x is equal to 1. So we have that. And here we are saying that since when you make your necessary substitutions here, you have x, this is 2y, but this is x plus 3. So for us to do that, we can just try to express this in terms of the point that we are going to be concentrating on here. Since it is about x is equal to 0, since it is about x is equal to 0, rather x is equal to 1, you end up with your x minus 1 here. Of course, that is equal to 0. You're going to concentrate at this. So the best is to express this in terms of an identity. That by identity, I mean you rewrite this in a form that when you simplify it, it gives you back this very term. But that new modified write-up should be in terms of x minus 1. And that is the term we have here. This one here. That this is exactly the same as that. So this is simply an identity. I am a black man, but tomorrow you can find me a little bit colored, but I am still Joseph Semdiva. You find that I have not changed. Sorry about my blowing of the nose. Fortunately, you are far away from me, so I can blow them recklessly. After all, my video is not on. No problem. At least that is one advantage of virtual classes. Even if I blow them, you don't worry about corona. After all, who am I not to blow them? If the president can take his cup of tea while making noise, I can also blow, and mine is uncontrollable. So apologies to those who get offended when I fail to control the kutiamara while having this lecture. My sincere apologies, but I can't help it. Right, we can continue. So I was saying that this can be expressed in terms of, this is an identity. In a layman's language, we would call this an identity. So we have x plus 3, but we can write this as 4 plus x minus 1. Of course, you know this minus 1 here is going to take that 4 to a 3, which will become a 3. plus x. Okay, so to avoid that mess, so that when we get a substitution, a suitable substitution for t equal to x minus 1, then this substitution of t equal to x minus 1 also affects the non-homogeneous part of the function of our second order. So that if we have this, instead of writing it as x plus 3, we simply write it as 4 plus t here. So we just kind of figure out logically, with the logic and reason, we come up with an identity. This is an identity. Identity implies things must be the same. So analytically, computationally, if you try to look at the left and the right, they are the same, though the appearance seems different. But if you simplify what you have on the right, you get exactly what you have on the left. Thus, categorizing this as an identity. So what we have, instead of x plus 3, we write it as 4 plus x minus 1. So that when we deal with the about to x equal to 1, which is x minus 1, when we substitute for this x minus 1, we also substitute for that x minus 1, so that at the end, this entire non-homogeneous differential equation will be represented in terms of t. All right, so that is what we are doing here now. So how do we go about that? It means we can have this rewritten. So we are saying if we let t equal to x minus 1, that is what we have here. So it means you'll have, hey, what is this? Now I'm not getting this one here. I think there is something I'm probably, things are not making sense. Am I on track? Okay, thus x is equal to 1 plus x minus 1. Okay, this is another, they are just demonstrating. If you say x, of course, this 1 goes with that 1, you get the x. This is trying to add some meat to this one here. I think that is what is happening. If you have x minus 1, you have x which is 1, 1 minus 1, 1, that gives you x. Okay, let's just change variable and then we substitute back, because now what I am interested in is that term, but how do we get up, how do we go about that? There is too much of the write-up here. This is just change of variable. I'm going to show you what that means, but if you follow what I have just said, you are going to end up with this term here, the one I have circled. So we rewrite this. So this one here is what you have here. Hopefully we are together, guys. This one is this one. So it is y prime prime, which is that one. Now remember, this is x. But we are writing x in terms of x minus 1. Remember here it is about x is equal to 1, which is x minus 1. Of course, that is equal to 0. So because of that, we have this x and we are saying this x is the same as this one here. We have just explained that right here. Where is my eraser? There you go. It is this one here. So instead of writing x, we'll also write x as in terms of this identity. So we convert. X will now be 1 plus t, because this 1 and minus 1 will cancel, so that is x and x. So we have two identities. We have this one here, and we also have that one there. Let's first of all clearly get to see the identities. So there are two identities, this one, and then there is this one here. So those are the two identities, this and this. And how have we done that? Where we have x, where we have x, we will substitute, maybe I change, okay. Where we have x, x will become this one here. Huh? But when it becomes this, x is going to become 1 plus x minus 1. That's why you see this whole term here is that one there. So this x now has become, wait a minute, where? So the x is now this term here. That is that one. This is the x. So what you had as x has now become 1 plus x minus 1. Remember, the 1 minus 1 gives you a 0, so you remain with that x. This is exactly the same as that. That's why I'm calling it an identity. Okay, then what we had as x plus 3, which x plus 3, we said would become this one here. And now this one has become that one there. It is this one. I think we are clear also there. Now, remember x minus 1 is t. X minus 1, we are saying let this one be a t. So that's why you see where you have x minus 1, it is now 1 plus t y prime. This is plus the 2y plus 4. Then where you have x minus 1, it is t. I think we are good to go, guys, there. Okay? Now we need to change. There is a change of variable. Remember, okay, we have one last change to do, and that one is going to come from here. Now, guys, remember our initial conditions are here. For example, I'm going to take the first one. Maybe I first remove this whole thing, and I refer to this one here, the first initial condition. What does the first initial condition say? The first initial condition says that if x is 0, if x is 0, what is y? Y is 1. But remember now, this thing has been taken into t. So what is t? T is x minus 1. So what does that mean? It means that if x is 0, so what happens when x is 0? You throw it in here. If x is 0, what do you get in terms of t? So here we are saying if t is x minus 1. So here x was a 0. So we are going to substitute. And what I'm trying to explain here, it is what you are getting. I think I need to highlight it all the way from here. This is for x is equal to 1. Y, oh, no, I am making a mistake. Sorry. The mistake is a simple one. This is not 0, but rather a 1. This one here. If x is 1, sorry about that, y is 0. If x is 1, y is 0. So we substitute. That's what I was trying to highlight somewhere here. That is this statement. That is the whole of this one here. Okay? Here we are saying that if x is 1, so we will substitute here. What would this be? It means that if x is 1, you substitute 1 there, it means it will be 0. Remember, this is y. This is y as a function of x. and it is now being mapped into y as a function of t. The x is being mapped into a t. So you have this function which is being mapped under those conditions there. So it means if x is 1, I throw 1 here, it means now it will become y 0. And that is this one here. So if x is 1, y is 1, it means for tx equal to 1, t will be 0. That is t is 0 when y is 0. So it becomes y is 0, which is equal to a 0. Then we do the other one as well. This is, where is the, okay, it is right here. I'll just change the color to red there. So now we have another one here. If t is 1, that is the same story here. So t is 1, y prime is 1. If t is 1, comma y prime is 1, okay? So if that is the case, we come and we substitute here again in this. So what is t? If x is 1 or not, t is equal to 1. If x is 1, so we substitute here 1, it means that our y prime, which was y prime 1, it will now be y prime 0. It will become, because the y, this y1, when it is 1, remember it is now yt. The t becomes 0 when you substitute this x equal to 1 into that one there. So it becomes y0, which is equal to 1, that same one there. That is the new change in the limits, which you see, this one here. Initially, the limits were, as you see them here, if I consider them, or rather if I take them in black, so these conditions here, they have become these conditions here. Okay, so once you have successfully transformed this, now you are going to compute. And when you compute and you get this whole thing in t, you can take the x back. But remember, you'll have substituted these conditions in there. That is what is the key in this example here. I think that was the only step that was bogging us down. Now that we are done with the bog, we can continue normally. Now here you continue normally, you continue, and continue, and you get the answer as this one. So you, my Zoom engineers, you get that one there. Remember, you are going to get things in T. You have got the constants, the coefficients. You follow the steps I gave you in the previous example. You substitute, and you are here, my Zoom engineers in training. That one is finished. What are the comments here? Oh, this is exercise for you. Wonderful, wonderful. And there are some few things here. Okay, these ones generally lead us to the next step. These ones. That sometimes these problems can be so huge. And they have some funny terms like this one. You can have funny terms like those ones. Then those ones. We are saying if you have all of these bizarre terms that may complicate the approximation, then you can use the Maclaurin's series expansion, which is that one there. Right. Before I continue, I see some questions in the chat. Let me see. You know, sometimes these chats you find people are talking to each other, sorting themselves out concerning these things. Okay, the idea is to, what is this one? This is Kasirie. The idea is to make the point of concern is 0, not 1. Initially, x is 0, 1, but if you substitute, then that one. D not, this one, by the way, it's non-homogeneous. And that is the problem. Thank you, Mr. Kasiria. This man, Kasiria, I should add him some 10 marks in coursework. I like the way he helps me explain stuff to others. Then there is this man, Mark Matiop Jola. He says, but the outcome is the same because, yes, what you are calling the outcome is the same is what I am calling the identity. Mr. Mark Matiop Jola. So when you substitute, you all right. I think he has Mr. Mark or Matiop Joel. When you say 4 plus that is that one, yes, the x minus 1 is, I don't know what the problem here is, but I think you have understood the point, Mr. Matiop. This was Kasiria trying to explain x is equal to 1, not x is equal to 0. Yes, Kasiria has explained it to you, Mr. Mumbere. This is Matiop again. It must be put to homogeneous part in that format because I tried it out without using the identity and I got the same solution. Yes, you may have tried it without the identity. I insist. If you are lousy, use the axe. You sharpen it. So for me, I am not lousy. I use the identity and things flow very fast. You go direct, you get the answer, no problem, Mr. Matthew Pujol. Those who can play with the identities, good for you. You can't play with the identity, you are better off going with it the way it appears, no problem. Right. Okay. That's exactly what he's doing, but in a different way. So yeah, you are correct. This one is saying what of tx minus 1? This is simply a pack of confusion being preempted among colleagues, which is good. Keep up the spirit to those who are trying to stand in for me. These days they say kuyiwaho umubiri. Some of you are really doing a good job in kuyiwaho umubiri. The kingdom of heaven is waiting for you. Thank you very much. Right. I think I have cleared everything in the chat room. Okay. So since I have cleared everything and according to Matiop Joel Mark, I think you have done probably some of these numbers. Please go and exercise solve these numbers. Frobenius, we have something called Frobenius. Frobenius is an extension of what we did. You guys remember we talked about solutions near regular and singular points. So I am going to rush through this one. And now you are already familiar with the approach. So in this case, by the way, am I recording this thing? You know, there was a time we jumped off. Okay, it is being recorded, good for us all. Right. So we have already discussed. So what is new in this is we are going to talk about this approach. Frobenius basically preempts some of the would-be challenges that one would bump into along the way if the computational techniques were quite become quite self-limiting. If the function I had unmuted myself. I think that is what Cassidy was saying. Audio is off, please. We can't hear you. Yes, I was also not hearing you, but now you can hear me. If you can't hear me, you can simply tell me that tumbiza sound, and I will do the tumbiza. If you want to hear me and I blow out your eardrums. Can you hear me now? You write here and you say you can hear me. Can you hear me now? You write in the chat room. Yes. No needless to kutumbiza. Mombere, do you want me to do the tumbiza thing? Tumbiza sound. Okay, this is according to Kafelo. All right, let me do the kutumbiza. But someone says don't kutumbiza. Okay, I will maintain the sound I have been, rather the volume. Okay, so we are saying that well, I had preempted some of those things. You people took long to alert me that the thing was off, but the preamble is quite direct to someone who has been following since we discussed these singular points. All right, so I said that if we have functions that we have functions that may be self-limiting, whereby self-limiting due to the nature of the techniques so far discussed in approximating these solutions. So if those methods are a little bit challenged by the nature of the functions to the extent that the computational kind of effort would be inadequate in achieving the solution you are seeking to achieve or analyze critically, then we are saying there are some other approaches that can come into play. And those approaches, they were first of all studied by Frobenius, but he looked at generally what we call Euler's coefficients. And these are the Euler's coefficients that we have been referring to here. So in that, we are saying from what we have done already, if you have an equation, this is, remember we had A2 from the generic one, that is 1.27. We wrote it in terms of Euler's coefficients. That is the A, the B, and the C. That is this one here. Then in here, we are saying, are they analytic at x naught? So we are saying, then from the definition, the point x naught is a regular singular point if both, this definition you already know, and the analytic at x naught. Thus, if x naught is 0, 1 point, if it is about x is equal to 0, this one and then that one, then 1.27, which is this one here. We are saying it can be written as this one here. So there is simply a change of these coefficients. So what was A here, we are writing A in terms of px, then we are writing our B in terms of qx, and we are writing our C, that is the Euler coefficients, this one here, in terms of Rx. Is that okay? And where we are emphasizing that the Px, Qx, and Rx are all analytic at 0. That is on condition that P0 is not 0. Why do we emphasize this one here? Of course, where is my, I need to write at net, okay. Here you go. What I'm trying to say, we are trying to emphasize this one here. We are saying P0 should never be 0. Why? Remember this, you can divide this by this whole thing here. So if this is 0, this whole equation here can go to 0. Remember, if you have y prime prime, if you remember what we did when we are talking about regular singular points, we divided these coefficients for y prime and y by that coefficient. So if this is 0 and you are dividing each of this by 0, then it makes this whole thing undefined. So that's why we are saying the analytic at 0 and P0 should never be 0, so that we have at least one solution of the form. Because if it is 0, then none of these solutions can ever exist. We are picking this from what we discussed. So if that is the case, we are saying if you let Px, one of the Euler's Fourier coefficients, if you let it to be defined as a power series solution, which is this one here, then Qx to be defined as that power series solution, and the Rx as that power series solution. And we are saying you let this P and that Q and that R to be power series of that centered at 0, then we can use our definition. It means that if we let y equal to x to the r, remember we want to generalize this. For example, this is x squared, but this power could be any other thing. That's why for us we are generalizing. But if we take it to be x to the r, this one here. So we are saying in that case, you can have y, which is xr, sum that, then you can simplify this one here. This, you can take this xr inside. This is x to the n, this is dot x to the r, which is xn plus r. This xr, we are picking it from, that is what we started with in the preamble, up this way. That in this case, the solutions are of the form y equal to x to the power r. And this is the preamble I was trying to explain when somehow I was muted, so you couldn't hear me. And you are saying this gives an equation in R that produces solutions with fractional or negative powers. Remember, this power, R, could be a fraction or it could be a negative. And you remember when we had these negatives, some of you who still remember what we did in the engineering math 2, we talked of the Cauchy Euler equation. I hope you still remember. Do you guys still remember us discussing the Cauchy Euler equations? I think you still remember that. So some of you who are crammers, you are engineers, but you are in these classes busy cramming. It is very unfortunate. We talked of this Cauchy Euler equation is last semester. So what I'm discussing here is not new. I'm simply picking from what we did. So some of you who are engineers but cramming, you are in disappointment. Even the structures you build, they will also be full of cram work, and they may end up crashing on the people. But if you didn't cram, then you remember Cauchy Euler. And remember when we dealt with the Cauchy Euler, we are still looking at some funny powers, mostly powers that were of a negative nature. If you don't remember, please you revisit those notes. So Here we are saying from the methods we've looked at, the powers, we didn't have negatives, neither did we have what? Fractions. So if we have fractions, then the question is, how do we go about that? That is what we are trying to explain here. So we bring in that power. That's why we are saying here that now if we let y, be this, then we can simplify this to be that one there. That is the normal thing. Then from this, we can differentiate this one. Remember, the other one is the second order. So you differentiate this. That will be y prime, which is a sum n plus r, that one minus 1. Take the second derivative, it is this one. You have this, then into this power here comes there, which is that one, and then this one minus 1, which gives a minus 2 there. Once we have this, we substitute these guys. The ones who may be in the background gossiping, we are now going to substitute that into this equation here. Where is it? We are going to substitute into this equation here, 1.28. What we are getting there, we are going to substitute. Remember, there is y prime prime, there is y prime, and then there is y. Remember, we have already got the coefficients of these Euler coefficients in terms of power series. So Rx, Qx, and Px. So I want to substitute in 1.28. If you do those necessary substitutions, by the way, be mindful, guys. This analysis we are doing, I am still talking to the crammers. You know, crammers are there to study, get papers, and run away without comprehending stuff. We are going to use this in solving the legendary equations. And those ones, they are applied heavily in approximations in your areas, you guys. Especially when you do this structural analysis, beams, you can have some intertwining kind of beams, and you realize that when you do that kind of analysis somewhere, you may have to do some approximations, but the approximations must be precise. So despite the fact that there will be approximations, you can use a combination of these power series solutions with the legendary equations. Some pronounce it plural as legendary. And then you approximate, you use this in your structure analysis. Especially when it comes to would be complex or abstract beam structures. So that is one key application that you engineers are going to bump into. Okay, so when I said we are going to substitute into this equation here, that was 1.28. So now that we have got the first derivative, the second derivative, we substitute, guys, back into this one here. We substitute into this equation here. So when you substitute, you have the x squared, this x squared here. I think you can see that. Then you have the px. What is the px? Remember, we had taken the px to be the sum. That is that one there. Then we have the y prime prime. The y prime prime is this one here. You throw it there. That is that one. Then we have x here. The x is that one. It is this one here. Then we have qx, but qx is this one here. I'm hoping you guys are following. There is this qx, but that qx is this one here. So we substitute the x, this x is that x there. Then the qx is this qx, the sum here. Then we have the y prime. The y prime is It is this one here. It is the whole of this. Throw it there. Then we have the Rx. Rx is this one. It is this one here. So that Rx is the next step that we do here. Our Rx is here. The Rx is here, guys. We substitute it there. Then y. Yeah? Remember there is a y. So the y is this guy here, which is this one here. For me, once we get here, these other things I have already mentioned them. Everything is now you are going to concentrate on these things of different powers. You concentrate on this one here. Those ones you are expert in doing. So we are saying, how do you minimize or rather solve those ones? So we are saying you can first of all introduce a term. We are saying you can introduce a term in here. We have already made the necessary substitutions. That is this one here. So we are saying, what if you multiply all through by x minus r? So if you throw this x minus r into this whole thing, of course, this one is going to help you simplify this. So if you take that in, that would be good news. One, there is x to the 2. You guys, you need to be alert now. I'm hoping you are very alert. So first of all, there is this x squared, then there is this x here. So this x squared here is going to cancel with this negative 2 here. Remember, it is x squared. The 2 will go with the 2. But now remember, you are bringing in x to the power minus r. So if you bring here x to the power minus r, this minus r here, this minus r is going to cancel out with that positive r. So if it cancels out with that positive r, you remain with simply x to the n, which is this one here. Hopefully I am clear there. Then you bring the same x to the minus r, you bring it here. So here there is some x to the power minus r, and you are multiplying it here. So what happens? There is this x here has a power 1, guys. Please be alert. There is this x here, the one I have underlined with the red. That x to the power 1, remember this x, it has a minus 1. So you have x to the n dot x to the r dot x to the minus 1. Now this minus 1 will go with the power 1 here. Hopefully we are together. So this minus 1 will cross out with that x. Then you have plus r, but this is minus r. So you realize that the x to the minus r here will cancel out with the plus r there. Then you remain with the x to the n, which is this one here. Then you come to this one. But remember, we said you are multiplying all through by x to the minus r. So if you bring the x to the minus r here, that is times this minus r here, this minus r, this one here is going to cross out with that r. And what are you going to remain with? You're going to remain with the x to the n, which is this one here. Now, if you are there busy cramming and you are not following, trouble. Now, If you have understood me there, we can now preempt the rest of this thing, which is easy. Now, if you look at this is x to the n, this is x to the n, everything is x to the n, the power is the same, power same, power is the same. That is one beautiful thing about this thing that was looking very ugly. Then the lower limits are all the same. It is n0, 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 n0. That is beautiful news. So if that is the case, it means now that one can be simplified further. Given that the power is the same, the limits are the same, the powers of x are the same, and the limits are the same, we can just simplify this one here. Okay, and that's what we are looking at now here. So in simplifying this, we are saying when we equate constants in 1.3, this one, constants, all of those to power 0. So when we talk of constants, equating constants in terms in 1.3 to 0. So just pick out the constants and what are these constants. So firstly, you can throw in a 0 here. If you take in, because we are talking of the 0 here. So if you throw in a 0, this is going to give you P naught. I'm hoping you guys are with me. If you substitute a 0 here, just throw in a 0, this will be P naught, that is the P0 there. Remember, x to the 0 is 1, so you simply get the P naught here. Now, you have this whole thing here. Remember, n is 0, so this is 0. You remain with the r, this is 0, you remain with the r minus 1. I'm hoping you guys are with me. I think I need to do some write-up for people to follow. This whole thing here is going to become r into r minus 1. Hopefully you guys are with me. This whole thing here, the one I have underlined, that is the r into r minus 1. But remember, here we have a Pn. But the Pn, remember, we've taken it to 0, so this becomes P naught. Remember, the sum is the same, so I can just take this and multiply it with that, and the same summation sign here. Since the sum has the same limits, and the powers of x and the powers of x here are the same, so you have that is this one here. But remember, this one has some n naught. There is this a here, which is a naught. The xn here, x is 0, so this is 1. So this whole thing gives you this one here, which is basically this term here. This term is exactly that one there. You do the same here and here. I think I don't have to waste time here now. So when you throw in 0, this one will give you Q naught. This is 1. Then you have here, this is 0, you get R. This is Q naught, R, N naught. The N naught we talk about is this one that has been factored out. So that is Q, R, N naught. The N naught is this one here. But this is RQ naught. So we started with the R, that is the RQ naught, which is this one. Then we come to the last one. This one is R naught. This is N naught here. So that is the R naught. That is this R naught. Then we include and we factor out the N naught. But from this, it is obvious N naught cannot be 0. We are trying to avoid the trivial scenarios. For N naught to be 0, this whole thing perishes. So since this can never be 0, we end up with that situation. We are saying R can't be 0. Remember here we say either this is 0 or that is 0. So since it is either this is 0 or that is 0, this can't be 0, so we take the other one to 0. So when we take this other one to 0, that is the term here. That is the PR, the P naught R minus 1 plus RQ naught plus that, which is 0. And we are saying if we express this as a function, which is rho R, this is rho R, and we express it as that. I think the simplification is probably clear. Then we can take a conditions here, because when you have something like this, if you simplify it in terms of R, you will end up with some quadratics in the R. Remember, when you multiply this R with that one, you can end up with the R squared. If you look at that, those first two there. So that is what we are referring to as an initial equation. This one here, this equation is referred to as an initial equation. I think when I edit my notes, I will label this equation, and then we say equation 1.31 is referred to as an initial equation. Okay, and this is of second degree. Why second degree? I've already told you, when you multiply this R with that R, it gives you R squared. That is this part here. Where? That since PR, rather rho R, is a second degree polynomial, then there are two values of R denoted by R1 and R2, such that PR, rather rho R is 0. When we talk of this, we are simply saying we can establish the roots of that one there. Okay, and we are saying these are known as the R1 and R2. They are known as the initial roots or exponents of the differential equation at a regular singular point. And the assumed solution, this one, which we have been discussing since we started, we are saying the solution, this one, we are saying that it takes a form that depends on R1 and R2. And once you have understood that introductory part, remember these R's have their funny types. They can be repeated, they could be complex in nature, and at the same time, they could be distinct. So how do we discuss those cases of distinctiveness, repeatedness, and then the complex nature of the would-be emanating roots? So here we say from the initial equation, we have the first case, R1 and R2, if they don't differ by any integer. When we talk of differ, of course, if they differ, it means they are distinct. Because if they are repeated, then it means they do not differ. So if there is a difference between R1 and R2, that shows that R1 and R2, they are both unique, given the fact that they differ. And if they do not differ, then it means, what does that mean? It means they are repeated. So here, the language we are using is not exactly what we used in engineering math 2. So they don't differ. That would basically imply that they are repeated in nature, because it means they are the same. So case 1, initial roots R1 and R2 do not differ by an integer. If they do not differ by any integer, we are saying if R1 is greater than R2, here we are talking of an integer. It means they may differ by something else. You may find the difference is 0.5. If the difference is by that, this is not an integer, it means this is a fraction of a half. Then it takes us back to the justification to why we are doing this. For those who have been following since we started, that this comes in to cater for scenarios that may exhibit fractions and negative powers. So if it does not differ by an integer, it may differ by something smaller than an integer. Clear here. Okay. That is this part here. Hey, where are we? We are here. Yes. If they do not differ by an integer, we have r which is greater than r2. It means r1 minus r2 cannot be equal to an integer. In that case, we are saying the first linearly independent solution will take that form. That is the condition. It will take this form. Now, this form you are already familiar with. I need to change the colors here. You are already familiar with this one here in red. This one you are familiar with it. This is at x will equal to 0. X not equal to 0 will end up with this scenario. So you know how to deal with this. So we are saying, and y2, what about y2? This one is simply for R1 because remember, these ones are distinct. They differ, but the difference among them is not an integer. So what we are trying to say here that it is a fraction. So the first would be linearly independent solution. Y1 would be of that form, and then y2 would take this form here. Is that okay? Here we are saying with b naught equal to 0. Remember here, given that we have these roots and we are going to be initializing. Remember, you start at n equal to 0, but now when you solve these equations, remember in the first case when we would take on the different values of n as we expanded, we would end up with the recurrence relations. This one I'm going to shortly explain why the first one we fix it at 1, and but this one here can be generic in nature, by the way. It could be any other thing, but for simplicity purposes, we can fix it at 1, and I will preempt that in the example. This is example 1.5 that we are going to do. Okay, so let's quickly, the example is not long, guys. Remember, most of these things you have already done. So we are just bringing in these 2 new techniques, and the rest should be okay. And once we finish this example, we call it a lecture. So the example is not long. We should finish it in the next probably 7 minutes. And then I answer your questions. I see there are some questions in the chat, around 6 questions. I'm going to deal with those. Keep writing your questions there. I'm going to preempt them. Let me just finish up this example. Right. We have this example here. I'm saying the techniques are the same, but the only things we are going to be mindful of are those powers. These ones here. That is the difference. So this is where we bring in the concepts of singular points. Okay. So here we have sort of the differential equation, this one, near the point x will equal to 0. You know what this means. So this is what we have. Where is my, okay. Near x is equal to 0. This one we know what it means. So we let y equal to xr, then sum. This one, you know where we are getting this. This is what we did when we are substituting. When when we are substituting into this first supposition, we pick it from here. You remember when we are expanding, we started it here. Yes, somewhere here. We said that let this part here. This is where we started, guys. We said that let y equal to this, and then the x to the r, we threw it inside, and we ended up with this one here. And remember, when we did this one led to the derivations of the initial equation. So when we started it there, we went as far as from this was the beginning, we substituted for the Euler coefficients. We used this term to simplify. This is a negative power. To simplify this, and we ended up with this initial equation, and we ended up with the initial roots. And from these initial roots, we are discussing case 1, which we have said that the two linear independent solutions would be given by this and this. And from that, we are discussing the first example with respect to case 1. So I guess now when I say let y equal to this, no one is getting lost. This is how we derived those equations up, which we've called the initial equations, and we ended up here. The Kuramas and the Gossipers. Hopefully you are that. Okay, so let's continue. So we are saying if this is the equation we have, the other methods are all the same, guys. I'm really not going to waste much time here. Let's not bog each other down. I'm sure you are now comfortable. So we have this. We have just explained this, why we are taking this. This is based on our derivation in the previous illustration. So when we have this, we differentiate this twice because this is the second order here. We have this and that. This is normal stuff. Simply take the xr inside. It is n plus r there. Differentiate once, twice. After this differentiation, substitute back into this equation here. So you have 2x squared, this one here. Now that you have the 2x squared, this is y prime prime, the y prime prime is this one. You throw it there. Then this is, you have to expand this one here. Remember this one is x y prime minus x squared y prime. This part here in the red. Just this thing without the minus y. This one here gives you that thing. That is what we are substituting here. We have expanded this thing here. So we have the first x, this xy prime is this one, x into sum n running from 0. Remember the y prime, we have already got it here. It is this term here. This one we substitute it into there. That is the x. Then this thing, this series, which is that one. Then minus x squared. The minus x squared is this one here. Then it is again y prime, which y prime is this whole term, which is that one there. Then we say minus y. Now the minus y is this one here. This is minus y. And that minus y is this term here. This one here. Which is the one that comes from here. Remember, we let y be that one there. The Zoom engineers in the training, I think you have followed me here. Right. So if you have got me there, we can continue and we simplify. What happens next is a simplification now. This implies this one. You can take the other coefficient and you simplify this thing. So from this, you can take those things in, you simplify them here. Then we are saying setting the coefficients of the lowest power of x, the lowest power of x to 0. What does that mean? When we say the lowest power of x, since this thing runs from n0, you can simply take n. If you remember n guys runs from 0. Our n runs from 0. So where is my, yes, there you go. N runs from 0, 1, 2, all the way. That is what we have. So we are saying when we take the lowest power, that is n is equal to 0, just like we did in the derivation of the initial equation. If your n is 0 here, remember it starts up this way. Hopefully we are together, guys. So n is 0, this one is 0, so it is out. This is 0, it is out. This is 0, it is out. You have that. So you'll have 2r, that is the 2r here, because firstly, this whole term here, it is going to become r into r minus 1. R minus 1, and this one is a not. Hopefully we are together. But now remember there is this 2 outside. So when you take this 2, you bring it here. That is the 2r into r minus 1 and not. So this is this term here. That one. Now we come here. We are taking n is equal to 0. We are substituting the first one. So in here, n is 0. You have r n naught. This is r. This is n naught. But remember, this one is also 0. Remember here when we took this one here, when we took the n. This is x to the 0. You remain with x to the 0, then x to the r. But now we are saying if you take the lowest power, now the r is going to take up those powers we are dealing with. Okay? So you now come to this one here. How do you deal with this one here? You do the same. That is r n naught. But remember here you can take in the other x to the minus r. That one can take out this one here. It can kick out that one there. It will kick out this one. It will kick out this one. You can simplify it until these powers are all to the n. That simplification you can do. That step here can be omitted. But if you want, you can include it there. Remember the other one, we multiplied by x to the minus r. Hopefully you guys, you still remember that. And you can see if you throw that x to the minus r all through, that r goes, this r goes, this r goes, and that r goes. Then you have the x to the n minus 1. But remember, when you have r plus n, this can also be, there is a step missing here that can take this similar steps that we did that took this and this. Remember, you have the x squared. I think this thing we have not simplified it. There is a mistake here, but that one can be fixed, guys. If you go back in here, you see you remain with this xr, but this xr actually goes away if you take that one. Then you are going to have once the R goes, the R has gone, you remain with the N is 0. I think that takes away everything. You don't remain with anything from what I see. Yeah, that should be it. Okay, I think everything has gone. Throw in the X minus R. These R's will sort themselves out. Okay, so that step you can throw it in, you can punch it up. This one you can directly pick it from our derivation. We actually used it up there. Okay, so if you do that, then you'll get the R. We were here, I think. This one here, this one is a 0. So you remain with the R. This one is a 0. That is R N naught, which is this one here. Then you have R, this is X minus R. We will take out that one and you remain with the X to the N, but N is 0 because we are taking 0, which is X to the power 0, which is 1. So you remain with the R N naught. Remember this N is 0, which is that guy. Okay. All right, so that is that one there. Then from that one, you come to this one here. You are going to expand this and this. And when you deal with this one and this one, this is plus, then this is minus. So same story here. You have this. So when you have minus, yes, this is minus N naught. Okay, this I think can be simplified with this one. There is one big step that is missing here that can help us fix some of those things that are not coming out very clearly in terms of simplification. When you go through this, please first incorporate this one here. That should simplify that. Then we had the X squared. I think I needed to go back a little bit. I need to go back a little bit. Otherwise, I may lose some of you. Right here. So here we have X squared. Yes, okay. The X squared came in here, and that is how you got the plus 1. That one is sorted. And then this same X squared, okay, that was that one there. Then this one here, and that became a plus 1. Sorry. This is a 2, this is minus 2. This becomes N plus R, which is this one here. N plus R, okay? And then this would go with the minus 1. You remain with the N plus R. I think there we are good. Okay. All right. I think that is that. So now we are saying we equated to powers of 0. We have now this term here, N0. This is A0. N is 0, you have R, but the X minus R would take out that one. You'd get N naught. How many terms are these? 1, 2, 3. We have 1, 2, 3, 4. There is a term we are not accounting for. And I think that is this one here. We still have a term that is not accounted for. I think that is this one here, if I'm not mistaken. That one is this one here. Okay, that is this term here. Where is my eraser, rather pen? So we have this term here. I think this is the term I'm not seeing in our simplification here. there is a missing term. This one is for the first one. This one is for the second one, which was, I'm actually very far. Let's not go there, but rather come here. Okay, this term is that one. R A naught, this is R, that is naught, the minus R kicks out that, you have that. That is this one here. We are saying we are setting coefficients to the lowest power of x. Right, so lowest power of x, we would leave out this one here. Why? This is going to give us x to the 1, guys. The x to the minus r would kick out this one here. Okay? Then x to the 0, that would be this term here. This one would go. Remember, if it is to the 0, it is 1, but you have a 1 here, so we remain with the x to the 1. But we are taking the lowest, which is n0. So since we are considering those whose powers of x to the 0, you have this is x to the 1 because of this balance here. We ignore this term. This one wouldn't qualify in this one. This one wouldn't qualify. Then we have this one here, x to the minus r. This term here would kick out this one here, the positive, and you remain with the x to the n. Power of x to 0, that would be 0. This would be n naught. That is the n naught we are getting there. This one would be x to the 1. That's why we have the 3 terms here. So we end up with the 2r, r minus 1 plus r minus 1. You can take out the n naught. If you factor out the n naught, this is r minus 1, that term there. Okay? Then we say, since, if we move forward, that is where we are. So we are saying that since n naught is not 0, of course here we are saying n naught can't be 0 because either this is 0 or that term is 0. So this term can't be 0 because this whole thing will perish. We end up with our initial equation. Just expand this one here. That is the 2r squared minus r. This and this is 2r squared. This and this is minus 2r. Minus 2r plus r is minus r minus 1. When you solve for this, you have these 2. Now, if you look at these 2, we concentrate. So, the difference is not an integer. Why? If you look at this and this, you have minus a half and 1. The difference would give you, if you subtract those 2, you end up with a 3/2. And indeed, this one is not what? An integer. That's why we are saying, therefore, R1 is greater than the R2. So if you have R1 is 1, R2 is minus a half, and you compute the difference here, you end up with 3/2, which is a fraction. This is an improper fraction. Then the 2 roots differ by, do not differ by an integer. And we have 2 linearly independent solutions. What are those 2 linearly independent solutions? For these 2 linearly independent solutions, we are saying we'll have a y naught. Remember, we had this up there. We had these up here, guys. that if they are not, you have y1, which is x to the power r1. That is the first initial root. This is the second initial root. And you have this is sum, and then that sum. Okay? So we are picking it from there. So what we, I think I'm very far, right? No? Where am I? Okay, we are here. So this is where we are. We are saying that since R1 minus R2 is that, then the two do not differ. And in that case, we are saying we have two linear independent solutions. That is y naught, which is this, with the n not equal to 1. Remember, why do we take n naught? This one we have just explained. You remember the other time I told you, I'll tell you why. In this case, there is no way you can initialize n naught to be 0, because n naught being 0 would imply that this whole term here wouldn't also exist if n naught is 0. We try to avoid those trivial scenarios. So here it means that we can fix this one to go to is a 1. It could be any other thing. But since this one can be generic in nature, we can just take this one to a 1. And if you take it to a 1, okay, so I was trying to see what the people in the chat were saying, but I've seen they are sorting themselves out. I will go back there. That pause, I was peeping into the chat. Okay, just to make sure that I'm not leaving people behind. Okay, so I am saying that in here now, guys, we can't take this one to be 0, so we can fix it at 1. Why? The reason is clearly explained in this step. That's what I have just tried to preempt here. That it is either this is 0 or that is 0, but purely n naught cannot be 0 because that whole thing will disappear. So we'd rather take this one to 0 and this one never equal to 0. Since never equal to 0, we can arbitrarily, and the word is arbitrarily, fix it at n naught equal to 1. Then we go ahead to find our AN, and to find the AN, we do the usual thing. All that we have been doing was to determine these roots and then understand whether those roots do not differ. And if they do not differ, then we know they are under case 1. Initial roots that are distinct, but the difference is less than an integer. And we can see that this is the difference is 1.5, which is a fraction. So since it is a fraction, we are saying here that we can now go ahead. Once you have done that, the rest is the usual stories now. We go back now with our thing, very well knowing the nature of the solution we are targeting, because now you can do the necessary substitution. So we go ahead to fix this power here, you fix this one here, you fix that, you fix that, you go on. These are the oral stories. Everything here is what we have been doing. I am sure you are enjoying, because now whatever you are seeing here is similar to what we have been doing. And you go, you substitute the n, you substitute those ones. Then you have your y. After getting these things, you expand this thing here in terms of r. When you expand this one, remember this is to the power r1, so the n does not affect this x. That's why it remains out. We only expand this one inside the sum, which is that one there. But remember, n naught, we fixed it at 1, given that this one cannot be 0. After that, When you expand, remember R1 is 1. This R1, the R1, this R1 here is 1. That's why it is now X. Then we substitute. Remember the N0, we fixed it at 1. And I said that was arbitrarily. Don't you go there and you crack your nut, wondering where the 1 is coming from. It is arbitrary because the N0 cannot be a 0, given that that whole term would disappear. Remember what we are doing here is approximation. So when you do that approximation and you substitute into this, you end up with these terms here. These ones are derived from the coefficients A1, A2, and A3, which is this one here. So once you have this, you continue here, and we say, we have now Y2. So what is Y2? Y2 is given by this, XR2, then that. But now remember our R2, guys. The R2 is to the power minus a half. Remember we said, I think I have to clarify here in the note so that people don't confuse things. We mentioned that before we started. Before we started here. Yes. We said that the situation, here we have those comments we made. I underlined these things here, guys, that if you deal with in situations, it is handled by finding a few terms of Maclaurin. This is if you deal with some fractions and if you may have logarithmic functions. But in this case, you have, remember, R2 is to the power minus a half. So you have some x to the power minus a half. This is where this Maclaurin can come into play. And when we see, or when we deal with that Maclaurin, guys, we end up with this situation here. 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 So we are saying Y2 is XR2, that is the derivation we made. But what is the R2? This R2 here is the minus a half, guys, there. Then you expand. But remember the N0 is 1. Then you have a half. The L1 is a half. These ones we have already established them, guys, from here. A1 is a half, A2 is 1 over 8, A3 is 1 over 48. They are here. They are already here. So these are the ones we have expanded. And we are saying if you do that, clear here, if you do that and you substitute, then we are saying, but this whole thing can be simplified further. The whole of this, according to Maclaurin, it is this term here. Now, what we deal with here is S6 work. Here, I wouldn't want to go much into that. It is this, which is generally x to the minus a half, which is this one here, with the factorial notation. This is x2. So the people I handled 2 years back had the issues with these things. So what I did in these notes today, I updated them and I added those steps which I had missed, because I would reach here and I tell the guys, you go and use your A-level work. Then they would prove to me that they were engineers in year 2, but having no idea of the mathematics in A-level. So for you, because of Corona, I have decided to spoon feed you. So these steps here, I am simply saying this is equivalent to that, and it is equivalent to that. When you look at this term here, this one can be simplified, and that is the Maclaurin I am talking about here, that if you have e to the x I'll just explain this very fast here. If you have e to the x, if you expand this, it is going to give you this one. I think you agree with me. This is e to the x. So expanding this e to the x, it gives you that. Then what if it is x to the half? Then if it is x to the half, this is what you'll have. Because remember, the first value of x is 0. So e to the 0 is 1. So if it is x, this is 0 over 2, it would still be 1. That is the 1. Then you go to this one here. So where there is x, you have half, half, half. So that is x over 2 squared, x over 2 cubed. And when you do that, you have this one here. But what is this exactly equivalent to? This term here is exactly this one. When you expand this thing here, let me maybe just try to show you. You people, you have an understanding of real analysis from your engineering math 1, which was handled by Mr. Kayondo. Now, when you expand this thing here, you are going to get this series here. How? If x is 0, if n is 0, you are going to have 0 here. So you'll have 0 over, this whole thing to the power 0. Sorry about that. That will give you 1. This will give you 1 over 0 factorial. But you know 0 factorial is 1. So this is 1. Which one is that one there? Then you throw in n is 1. When n is 1 here, this will be x over 2. 1 factorial is 1. So basically this will give you x over 2, which is that one there. Then when n is 2, this is 2. So you have x over 2. The whole thing is to the power 2. This is x squared. This is over 4. But there is n, which is divided by 2. This is divided by 2 factorial. So divided by 2 is times a half. 2 factorial is 2, which is x squared over 8. The third one would be, now this would be power 3. That would be x cubed. 2 to the power 3, that would be 8. 3 factorial, that is 3 times 2, 3 factorial, guys. That would be 3 times 2. This would give you what? A 6, I think. So this will be times 1 over 6. 6 times 8, that gives you, I think that gives you 48. Hopefully I am right. If you multiply a 6, I'm very lousy with this simple computation. Okay, that gives you 48. So that is this 48. So literally we are saying that this whole term here is that term there, the e to the x. So what does that mean? This implies that what we had as, this is my mouse, what we had as this term here, it can simplify to this one, but this is exactly, but remember, I am saying that from here, that this is the same as e to the x. So instead of writing that whole thing, this whole thing here, I can just write it as e to the x. This is from Maclaurin. That is what I have done. So in the previous thing, rather step, instead of writing this whole thing here, I simply write x to the minus a half. Then the sum, the whole sum here is simply e to the minus a half x. And this is the solution. This is our y2. So our y2 is this one here. And if that is our y2, we end up with our final solution here. What is the final solution? The final solution is this one here. Remember the general equation from engineering math 2, we said y is C1y1 plus C2y2, which is this term. The y1, we got that, and the y2, we have got this one. If we had initial conditions, then we would do explicitly. We would have explicitly got the values of C2 and C1. Where did all of this come from, guys? As I finish in less than a minute, where did all of this macrorin? Remember, these are the exponential terms. That is where we started after finishing. That was in the preamble here, before these examples, that you may end up with the exponential terms, such as these ones here. You see those ones? Those are the ones we've been dealing with. And these ones can lead to what we call the macrorin. You can also have the cos and blah, blah, blah. But that particular example we've dealt with the e to the x, which is macrorin. And from that macrorin, we have ended up with this answer here. That is that is this one here. That is the final answer we have got right here. This is the one. Okay, I think that marks the end of the lecture. This marks the end of the lecture. I don't know, there is a number 2 there which you can solve yourselves, but we have had a feel of Frabelius, and we are going to use this one to solve a legendary equations. And I'm going to unmute you now for those who may have questions. And I also look at the questions in the chat, if there are any questions anyway. Maybe I first discuss the questions in the chat. At this time, I can unmute you. The gossipers, I had silenced the gossipers. So now I can unmute them. And you'll hear them making noise. Yes, there is a hand by Mr. Rodney Spencer. Let me unmute you and you ask your question. Yes, okay. I think now, if you don't have a question, please, this man, Irumba Kolini, you mute yourself. You saw I told you when I unmute, the gospels will all be there making noise. I want only Mr. Rudini Spencer to be unmuted and he asks his question. If it is still there.
Yeah, it's still there.
Yes.
The first question I had was, how do we know, like, for a particular question, it requires us to use the Frobenius method as compared to what we were doing before?
Okay, can I answer that one?
Yes.
Okay, if you saw the example we are dealing with there, it has the variable, rather the non-variable, the variable coefficient is x squared. So once you have that x squared and you go ahead to solve the roots may give you, they may be unique, but they may be in terms of fractions. And once they're in terms of fractions, remember when we did sort of equations in engineering math 2, you'd have those roots and you'd say you have, let me just try to write that here. You have e to the power r1 x, where r1 is the first root. Maybe this is c1, then plus c2 e to the r2x. This would be exponential, but this was independent of whether r1 and r2 they are fractions or not. That's why you remember there, even if you do get R1 is a -4, maybe the other one is a -2, we wouldn't give a damn. We'll just throw them there and we say they are distinct, and therefore the solution is that. But in this approximation theory here, because we are mindful of the nature of the root that we get, whether it's a negative or a fraction, given that you are approximating. These solutions, when you compute, remember we are summing, and be mindful that when we sum, we terminate at a particular value of n. We do not exhaust the n. That's why I'm using the word approximation. So the solution you may get may not be exactly one that you may have got if you had solved explicitly. You get me? So that's why we are saying that here, like you've seen in this example we have done, one R was minus a half, and the other R was simply 1. According to the methods we looked at in engineering math 2, we would simply say C1 e to the minus a half x, and then we would say plus C2 e to the x. But in this case, for you engineering students, actually we are going to look at some computational methods. Given that we are approximating, we have to use that Frobenius, and we have to be mindful of that macrolinear expansion to cater for these fractions that are not explicitly covered in the previous methods we have just discussed. Yes. Any other questions? I think the questions are over. And the venue I am occupying, it seems I have overstayed my tolerance by my boss. So I see some of you are still raising your hands. Irumba, maybe you ask your question, but I'm going to change the venue. No problem. The internet will remain on. Your question? Yes, Collins. This man is not asking the question. Okay, I think his question has been preempted. You people are putting up, those people putting up their hands, please go ahead and you ask your equation, your questions. I think I unmuted you. You have the hands up, I've cleared you to ask, but I don't hear the questions. And I see you are active. Cassidy Henry. Can you ask your question?
Yeah, excuse me, sir.
Yes.
Yes, my question is, I want to know the relationship between equations 1.26 and 1.27.
Okay, let me answer that question in less than a minute. Just give me a break for 1 minute, please. And I'll just mute you briefly.
Yeah, you can leave the
discussing. Yes, this is Mr. I don't know. Yes, Irumba. Irumba, you had a question. I think Irumba has disappeared. You can hear me, guys? Irumba, Collins. Can you unmute yourself? Collins. Irumba Collins. Right here. Yeah, tell us how that. Manifest. Yes, and you have no mask. Yes, Collins. Collins Irumba. Yes, Mr. Kasiria, your question. Kasiria, you unmute yourself. Kasiria, can you unmute yourself?
Yes, my question. I want to know how equation 1.27 comes to 1.28.
1.27. You said 1.27 comes to 1.28, 1.27 comes to 1.28. 1.27 comes to 1.28. You go, you check from outside. Thank you. 1.27 comes to 1.28. Let me just, okay. 1.27. That is page what? Can you quickly refer me to the page, please? 1. Sorry?
Page 14.
1.27. Okay. You're asking how does 1.27? Yes, I think I'm here. You're saying how does 1.27 come to 1.28? That's the question, right?
Yes, sir.
Okay, but your volume is so low. Anyway, I've got your question. So 1.27 is here. We have our 1.27, and we are saying that we could write this in terms of Euler coefficients. Now, we discussed this. You remember we discussed the Cauchy-Euler equations. This is the same equation we discussed when we are dealing with the Cauchy-Euler. So since this is second order, according to the Cauchy-Euler, if you have coefficients of this type, the first would be ax squared, then you have a bx, then plus c. So it is quadratic. The variable coefficients follow the order of the equation. This is a second order differential equation, and the coefficients would be of degree 2. This is since this is order 1 here, if that was not there, that is degree 1, and then the same with this one here. This is 0 because you have cx to the 0. So from the 1.27, remember we have attached this assumption that if these are Euler coefficients, which takes us back to what we discussed in engineering math 1, the Cauchy-Euler, we still looked at this. Then from that, it means we transform the A2x, the A1x, and the A0x into ax squared, bx, and c. That is from this one here. And then from this one we have proceeded normally. We are saying now from this equation here, we have got this one. The x squared you see here, it is this x squared. Then it is this a here that we are writing as the px. Then this x here is this x here. And the constant could be in the constant could be expression as a function of x, which we are calling qx. And then here we have a c, which we are generalizing as rx here. That is how the thing comes to this one here. And you can see even here we started by talking of a regular singular point, and we referred to this. Remember the A1 and the A2. These we discussed this when we started off this course. So you need it for you to comprehend this. You need to start from where we began, because here we are recalling this from our definition of regular singular points. You remember I gave you even some exercises. The handout has exercises, which is this one here, this part here. Okay. And then from there, we simply define now these coefficients, the px, the qx, the rx, in terms of these so-called power solutions, which is the 1.29, and then we proceed. Okay. I think there, I don't know, did I again mute you people? I thought I had unmuted all of you. Ask to unmute all. I think you can unmute yourselves, guys, those with the questions. Okay. I don't know whether there are other hands, but I think
yes, excuse me, sir. Excuse me, sir.
If I answer your question, you put your hand down. I think, Cassidy, I have answered probably your question. Yes, who was asking? Irumba, yes.
Irumba. Yeah, sir, I didn't get the explanation you gave us, like when are we supposed to use the Frabelius stuff?
Oh, but I have just, okay, can a colleague try to answer that? I answered that. I've just answered that one before I took on, what didn't you get, okay, from my explanation?
Like you said, when ax squared, but when I was trying to see that number too in the next number.
No, Mr. Irumba, I said I took time to explain. Maybe you went off. I told you that when we did this in the previous one, we are not mindful of the fractions and the negatives. But in this case, because we are approximating the solutions, remember I have already said that when you approximate, you sum to n, you never go all the way to infinity. You may substitute up to n is equal to 4, up to n is equal to 5. So we are mindful of those fractions that are derived in our attempt to get the roots of the equation. That's why you see there, we don't simply see repeated roots, neither do we say distinct roots, but we are discussing the distinctiveness in terms of the difference not being an integer. And any equation that results into a situation that may give you roots that go beyond a power of 1, then you have to bring or explore or use the Frobenius method to compute those ones. That is the difference. You go back and you understand the preamble. I have already justified that, and I am probably, maybe it is me explaining it poorly, but that's what I started with here before. Where is it? We finished those and there was an exercise, but before the exercise, okay. Yes. This is number 4. We finished number 4 and we came to this. I think this is it here. We had some, this is number 6, exactly, right here. This is the statement that introduced us to Frobenius, and you need to understand that, rather you need to read and understand this. You see this part here? This would call for Frobenius. This is in addition to what I have just told you. We dealt with the non-homogeneous term, and we are saying you may end up with the exponential terms like that. Remember, when you have those second order and you have powers, like the example we've done where it is to the power half, and the distinctive roots, they don't differ. So you don't have to use those Frobenius if the difference between the roots is an integer. You get to me? For example, if one r was 2 and the other r was, say, -4, the difference between these is an integer. So you don't have to worry about Frobenius. But so long as it gives a fraction, and okay, of course, we also worry about the negatives. This wouldn't also work. This negative alone would also call for what? For Frobenius. But if the difference between these is a half, rather is a fraction, and it is a negative, you have to go for Frobenius. But if the difference is not a fraction, and either of the roots is not a negative, then you can use the previous approaches we have discussed. Hopefully we are together, Irumba. Irumba, am I making sense? Irumba Collins. I don't know whether he has again gone off. You people allow participants to, I have kept unmuting you. So if you have other questions, you ask, else let me go to the chat. And I look at what is in the chat. We are muted. Sorry about that. I thought you were unmuted. Unmute me, please. Yes, I apologize, Collins. I thought I had unmuted. Good evening, sir. I did not so much get the simplification in 2.28. I would like to know how the third summation was not included in the coefficients. Okay, there is a question Gabriel is asking here. That is 2.28, that why didn't we include the third sum? Yes, I think I explained that as well, but I can clarify it further. This is 2.28. I think that's what the 2.28. Oh, okay. Where is that? 2.28. I don't seem to see the equation the younger man is talking about. 2.28.
So I think he meant it was 1.31.
Because there I've seen 2.28. 1.31. 1.31. H. I can't, okay, this is 1.31. Yes, this one. No, this one I explained. I told you that. Guys, I told you here, I came and I explained this one. And I told you that, remember we are saying, setting the coefficients of the lowest power of x, lowest power of x to 0. Lowest power of x to 0. So if you are equating, the keyword here is the keyword here is lowest power of x to 0. This one here. That is what we are discussing. So since it is lowest power of x to 0, so x to 0, first of all, since you have n everywhere, remember, if you simplify this by multiplying by x to the power minus r, we did that. This minus r would cancel out that and that. Right here, you mean? So I am saying that this is the book. Write your name here, rather here. So I am saying that this x minus r would take this out, would knock that out, would knock this one out here, and would also take this one out, guys. So your interest is in this term here. I think this is where your worry is. And I took time to explain this. You finished? Okay, here you go. You come in. Okay. So, we emphasize red. Now, in here, when we said x to the 0, so lowest power to 0, it means n, we substitute our n is 0, 1, 2, and we move on to infinity. So what we've done here is when we take the 0, we throw the 0 in. So we throw this 0 in, so the 0 is out here. What happens there is, when you substitute into this whole statement, the 1.31, which I guess you called it 2.28, when you take the first one, n is 0, so you take the n out, take the n out. This would be r into r minus 1. Then the an becomes a naught, but this is x to the power 0, which is 1. So you remain with the 2r, which is this one here. This is 2r into r minus 1, which is that a naught, which is that term there. But remember, be mindful that the n is to the 0. We are referring to this one here. Then the second term, this is out. We have r. Remember, we are throwing in the 0. So this is r a naught, which is this guy here. Okay? And remember, this n is to the 0. The x to the minus r took away those r's. Now we come to this term and you are asking, why haven't we ignored this? Rather, why didn't we include this? Now I am on this one. When we take n to the 0, n is 0 here. So this one is out. This is 0 here, younger man. Now this n here is also 0. But remember now, you had x to the n dot x. There is a power 1 here. So that is power 1. The n, I'll just clear this a little bit. Right, there is this x to the n, then there is x to the 1. So this is n. When you take this to a 0, you are going to remain with the x to the 1. But remember, we are considering coefficients that give strictly those whose powers would go to 0. So since this one remains with the x to the 1, we leave this one out because this one does not satisfy that condition. So we left this out and we went with this one here. From this, we jumped to this one. And we said, okay, this is already n, this is 0, that is n naught. Then we ended up with the n naught. We left this one because this one does not satisfy what we have imposed here, this statement here. Okay. I think that one is also answered. I don't know whether there are other questions, and I don't know whether there are others in the chat. That was Mr. Ai Gabdiel. I even don't know whether he's still on or he left.
I'm around, sir.
Okay. Have you got me? Have you got my explanation?
Yeah, definitely.
Sorry?
Yeah, I get you, sir. Definitely.
Okay. So now we have, when do we decide to use Frobenius? That was Mumbere. I have answered that. I think Irumba. Sir, explain more validities of Frobenius. Validities, I don't know what Irumba here says. Maybe that is the question I tried to answer when he said, we multiply through with x to the minus r at that stage to eliminate xr. Yes, I explained that. This was Mark Matiopijolo. He did that. That's what he said was a missing step. Okay, thanks, Mark, for helping me out there. Cassidier, for the initial equation, there is no need to do that just yet. That will be done later in the recurrent. Okay. Tracy Rodney, this guy had a question. Okay. Excuse me, sir, on equation 1.31, shouldn't we multiply? That one I explained, Mr. Tumwesije. Mathieu, we are voting on the constants. Okay, I think we have finished these. If n naught is 0, shall we have a trivial? This is Madame over Mr. Ampumuza Mukunda. That one I explained. Gabriel, I think the whole equation will die if a is 0. Yes, I is correct there. Okay, I think these are the questions somehow. Then there is Cassidy. Excuse me, sir, kindly clearly re-explain the relationship between 1.27 and 1.28. I have done that. This is a number. It's better you show the derivation. It will easily guide one to avoid the simple mistakes. That's my opinion. I agree with your opinion, but we did the derivation in Mumbere. So that example we have done was based on the derivation. And I concur with your opinion, and that's what we did. How do you quote Maclaurin without differentiation? I have not got that one, Mr. Makamatiopujolo. So with the DEs that involve terms that require Maclaurin, are we supposed to just quote them when they are in a paper, or we have to show their derivation? You sure? Highlight more about the combination of exponential, and we have done that one. Should I show how the coefficients of that are obtained, or I just substitute the expansion once? You show. This is Mr. Ocheng. Please show. These people, Irumba is saying Tumbi is a sound. This is Kafero. Okay, I think I have preempted all of the questions. All right, guys, I think we are done with the questions. For those who kept on up to now, thanks for your patience, and please go through the materials. I will organize another lecture through your coordinators, and it seems the coordinators are at large. Oh, Sonia. Sonia, unmute yourself and you say hi to me. Sonia? Madam Sonia.
Hello, Dr. Sewuliwa.
I thought you were already at large. You are still there.
Yes, yes.
What about the usual suspect, Mulindwa? I think that one has already disappeared. Mulindwa, surprise me. Mulindwa? Yeah, that Mulindwa, you know, is already at large. Okay, I don't know. I saw someone raising her hand through some person. I don't know whether people were sharing some of this data by sharing computers. Okay, guys. Okay, just maybe there is one thing in the chat. Thanks to, okay, that is Wafla Eric. All right, guys, thanks for the patience. Apologies for the delays for those who may have gone out of data along the way. But I really had to explain that stuff. Okay, we pick it up. You'll hear from me through Sonia and Raymond. Have a blessed evening and bye for now. Okay.